to Nana's dismay.
Oh, when Nana is next to Papa, it's Nana.
Oh, is it now?
Yeah, now it's Nana.
Okay.
All right. Closing the circles to the large language models. So we won't implement one from scratch. It's not that simple, although the basic ideas can be illustrated quite easily. Here, two papers to get started with. Attention is all you need. That's basically the breakthrough paper, right? We come to what it means, as well as GPT-3, its nature, scope, limits, consequences, all a little bit older, but when we talk about older in finance, we are still dealing with the papers from the 50s, 60s, 70s, right? So here when we say oldest, 2017 and 2019, right? So I don't know, somebody probably is tracking the number of AI, deep learning, LLM papers that are, excuse me, uploaded on archive. Sorry?
I said probably an LLM is tracking.
Yeah, probably. Yeah, sure. That's like going through all the text and being updated on a daily basis. And yeah, again, a little bit of text from our wonderful helpers, so they can talk about themselves like they're really egotistically. Right? So they know everything. Large language models like the GPT or BERT, we will apply BERT also in a certain context. Ernie and BERT here, right? Bidirectional encoder representations from transformers. Pretty long name. BERT is much more convenient, have revolutionized the field. So what we have done is, like the starting point today, we now go a few steps further, and as we have had before, a bunch of bullet points here, bullet points with regard to the techniques, characteristics, components of these models. So transformers is what is at the core. So in the paper, here you see it, attention is all you need. Paper consists of encoder and decoder stacks, though LLMs like GPT only use the decoder stack. Attention mechanism, scale dot product attention, computes attention score based on the dot product of query and key vectors. We come to that. With regard to the examples, multi-head extension, parallel attention layers that captures different types of information with regard to the text. Positional encoding, a very important element here as well. So they don't have the standard transformers don't have a built-in notion of sequence order. Positional encodings are added to provide the position information. We all know, and I would say German is one of the languages where you can do this to excess. You can have, I don't know, a 10-word sentence, and basically every combination of these 10 words still make a proper sentence. This is not true for every language. For example, in French, it's different. Other languages as well, they have much harder rules, but right, it's sometimes tricky, in particular also for kids or people learning the language, to come up with the most probable or the most often used sequence of words in that particular context, right? So not only problems that machines are faced with, maybe we human beings as well. Here, position sequence, also an important element. And when you, now beyond what is written down here, this is even in let's say the popular press, where they write, they have a look at a sequence of words and then they predict the most probable next word. Of course, this is something about the sequence. It's like our similar to the prediction task with regard to a Financial Times series, right? We have a look at the history and then we pick something that is, from the point of view of the algorithm, the most likely next step. But here we often have multiple choice, basically, and everything might make sense. This is what is then modeled with the temperature in these models, right? Where say 0, it's always the most likely one that is chosen, but this doesn't have to be the case, right? You can also have, so to say, randomness embedded, like a writer, an author, right? So, well, this word, not maybe take that one, gives a better meaning, better sound, change the sequence of the words here, right? Editing, of course, an important part in human text generation. Embedding layers, now we have our embeddings again. So input tokens that are embedded into vectors. Often initialized with pre-trained embeddings like Word2Vec, what we have used, so they can be trained from scratch, but often pre-trained embeddings are used just for speed up, convenience, etc. Layer normalization, normalize the activations of each feature. Stabilize, accelerate training, because when you read this, oh well, this model has 1.5 billion features, right? And they are so huge these days that everything that helps with efficiency, acceleration, of course, is something good and what people are after, right? Feed forward neural networks. Of course, neural networks play a role here as well. Residual connections, masking. Maybe we don't go through the other ones here. Pre-training and fine-tuning. This is an interesting and important part, right? When we have something like JetGPT, which is a general LLM, right? Fine-tuning allows you to train them to be good at certain tasks, right? So let's say you have JetGPT, but you can fine-tune it to be an expert lawyer, for example, to be better at answering legal questions, or you can fine-tune it to be pretty good at medical questions, for example, right? Also interesting and a very efficient approach, because fine-tuning can be done, let's say, with a relatively small budget. The training of these models, we know, requires in the hundreds of millions, right? Therefore, even OpenAI, as far as I can tell from what I read, they are not yet in the position, I don't know what exactly it is, but budget might play a role here as well to really go to GPT-5. Some say maybe it's there. I don't know, but budget, in any case, even for the large multi-billion-dollar companies, plays a role here as well, because it's so incredibly expensive today. And you might recall the, I'm just like, again, I wanted to make a connection to what I was teaching on Thursday. So there I was talking about the paper, the unreasonable effectiveness of big data, right? And in this article, it is pointed out that there are several domains that simply cannot be treated through AI and machine learning applications, like physics, where we say, well, in physics we have sometimes the wonderful situation that we end up with something pretty simple, concise, and beautiful, like Albert Einstein's equations, E equals mc squared, or basic mechanics like F equals m times a, and all these, right? It's concise, really, but it's truth about the world, right? Finance might not be something like this, right? In the past, people were obviously after these elegant equations. Think of the capital asset pricing model, pretty elegant linear equation, but has basically no practical use. And not to say anymore, it never had, right? It's simple, it's elegant, but it doesn't work. Just think of, like, I don't know, the physical theories, models, and equations, where they say, well, yeah, we have some equations, they don't work, but nevertheless we use them to design the next spacecraft, which we use to conquer the moon. Right? Different situation, or simple relative to maybe spacecraft, airplanes, right? You need to have proper stuff, but in finance, it was often the case, still up until today, and I've told Janet a couple of times, when you pick up older finance books, like Kuppel & Wesson, or the latest ones that came out, I don't have a good candidate now, they still have all the theories from the 60s, and they sell it still like this is the truth, right? So this has become, to some extent, a little bit like religion, like the Holy Bible of finance has, like, the capital asset pricing model, arbitrage pricing theory, etc. But the empirical support basically is zero. Anyways, that's not our point. I don't know how I got on this tangent.
Weston, by the way, does include the Bauman French and
The analysis with the.
APT. It does not have machine learning.
Yeah.
Could you imagine 1987 and had machine learning?
Yeah, now I know how I got to that. It's about the yeah, the big data, and that in this article, the unreasonable, you can Google it, you can download it, it's a nice read, short read, the unreasonable effectiveness of big data, and it actually refers to finance, at least to economics, where they say, well, maybe such disciplines are closer to natural language processing, right, than they are to physics, in the sense of that whenever humans are involved, the modeling is pretty difficult with, I don't know, atoms, particles. Usually you don't have humans involved, on that level at least, you don't have them involved. And therefore, here, in order to, for the companies, the models who have been able to crack natural language, they needed the gazillions of training points and the 1.5 billions of features, etc. And maybe finance is something similar, where you simply don't have these simple equations or systems of equations, the standard linear relationships that are assumed by ordinary squares, etc. pp. Maybe we need something else. That was the point coming from the large data sets, right? Adaptive learning rates, regularization techniques, stuff that we use in other contexts as well. Parameter sharing, large-scale training, here we have it. So I was now talking a while about this. Have hundreds of millions to billions of parameters. Training requires distributed computing, no surprise here. Prompt engineering, I think it was arguing about that part, right? I would love to see a prompt engineer who makes the 300,000 to 500,000 per year just for writing prompts for the machine. Maybe there are some. Knowledge integration, yeah, see, very interesting stuff, and this is, like we all know, developing rapidly and has been developing at a crazy pace, right? So getting to the final, second but last Jupyter Notebook here. And this is also, as before, more like a collection of elements that are relevant with quite a bit of text, one after the other, with some illustration to the text, if you like, obviously in the form of Python code, right? So transformers, imagine here, it's a nice example, right? Because like in reinforcement learning, I think here with regard to NLP, generally speaking, there's so many nice analogies that we can relate to as human beings, which is maybe not that simple when you say, well, what is happening in multi-dimensional spaces when you have a support vector machine algorithm doing stuff here and there. But here you have these analogies that help at least, right? So imagine you're reading a book, and while reading a sentence, you remember something related from a few pages back. 5, 15, 20, this connection helps you better understand the current sentence. Again, the example of a novel or a textbook, a science book, a finance book, right? It helps probably when you read chapter 3 to have understood what is in chapter 2. This is not always the case, so there's not a necessity, right? You can have also, I don't know, a collection of papers which are completely independent of each other, and other formats, right? Or poems. Think of a collection of poems. When you read the 20th, it doesn't have to be any connection to the first 5 or the next 5, right? This connection helps you better understand. Transformer does something similar, but for machines now, right? It's a method that helps machines to pay attention to different parts of data, like in history, around it, right? And to understand it better. You can look at words, at all words at once, and decide which ones are important in context. So, like Superman scanning it and seeing, well, here are like the hot spots that we need to focus on. And what we have done before is from a different angle similar, right? Where we have gotten rid of the stop words and, like identified keywords, and ended up, instead of 20 words total that we got started with, we got the 6, 7 words which were the keywords in this context, right? So the GPT now, we know the abbreviation for Generative Pre-trained Transformer. It's like a super smart student. Before giving it any specific task, it reads or trains on a huge amount of text from the internet. This is the pre-trained part, what I was saying before, right? You have this thing at one point, and later on, you can maybe add, you can fine-tune, you can do X, Y, that, right? So it's language, facts, reasoning, so it's like yeah, we don't have this anymore. I don't know. I recently read something when, and this was just only with regard to one discipline, probably mathematics is a typical example. When it ended that a single human being alive was able to have the complete knowledge of a field, master, right? Maybe Gauss, for example, mathematics, etc., right? This used to be possible at some point in time. Probably Galileo Galilei was able to do this with physics at the time, and many more examples in the past, but we have long passed the point where this is even in sub fields not possible anymore. And here we have something, the machine, which more or less can do it over everything, like being polyglot and acquiring a ton, never forgetting anything and seeing all the relationships, etc. Right? Now, once it is trained or asked for a specific task, it uses all of it and generates, writes, creates coherent and contextually relevant response. I must say, this is also from the beginning what really surprised me. I hardly ever do German, but every once in a while I do. But with English and German, I never saw a sentence which, standalone didn't make sense, right? Maybe it was not the right thing you were expecting or whatnot, but language-wise, it was proper language. I've never seen like spelling mistakes or something, right? Never, right? Syntax or what we were talking about, like the sequence of words. It's always proper prose, if you like, right? Other key topics, right? Attention, we have already discussed before, at least on the abstract level. The embeddings, here we have discussed a little bit more, right? You have your words, you put them into a high-dimensional space, so you get a numerical linear algebra spiral representation, the fine-tuning, right? Instead of having somebody who has learned a lot of things, one a doctor, the lawyer, the finance professional, whatever. Self-attention, a special feature, right? When trying to understand a word, the model looks at all the other words in the sentence, not just neighboring ones. So it's like reading a whole paragraph to understand a single complex word in it. So it's like, you have something like a distribution over everything that is in there, right? What is important, what is not important. Like when you see geography and there are a couple of, mountains, this might be the important words, right? Layers, tokens, right, and here, so the embeddings. And this is what I added this morning, therefore I've added here just discovered. It's a pretty nice blog post. It was attribution here in the weekly Python newsletter. And you see this was posted on 23rd of October, not brand new, but relatively new. And this is obviously an outgrowth of a talk that was given recently, and there are a bunch of things which are pretty nice and relevant and illustrative. Should rather zoom in a little bit here. Location and many multi-dimensional space, what we are talking about, right? We place it into 3 dimensions here that we can relate to, but much more here, right? Cosine similarity, many code examples. This guy here, I have never heard of him before, has even written a command line tool to interact with LLMs easily. You provide a token, and then on the command line you can do stuff that we have been doing now in the web interface. So I've provided a link. Maybe you find something here, like links to papers, packages, examples. Seems to be a pretty nice collection. I must confess I haven't read it from A to Z because it was this morning, more or less before I left. You see here, this is what the guy has written, pip install LLM, and then you have on the command line, you can do LLM. I think there is an example. Where is it? Here, like that simple usage, right? For those of you who work on the shell command line more often, you type LLM and then 10 fun names for a pet pelican, and GPT-4 gives you the fun names or whatever. Right? Might come in handy to have this on the shell as well, and not needing to navigate to the browser or to the notebook and hit the API. So embeddings, we know already a bit about it, therefore we might be able to go a bit faster over it. So fundamental concept. that we have seen already in action, dimensionality reduction, semantic relationships here also important in that context, transfer learning, so pre-trained embeddings can be used in new tasks. So we don't, in other words, don't need to reinvent the wheel all the time. So text is text after all. So if one model was trained on text, then the other model might be able to capture it. Or the same model in another situation doesn't need to be retrained, updated as well. So the examples that I had before were related to Word2Vec, but there are no big surprise, as it's often the case. We have other options. One option that I have added as well is here. This comes a bit later. Is using the pre-trained ones. So I don't know, this jumping around here with the clicking, I don't know what they changed there. Like BERT, and here you see also some other packages. So Python example with Word2Vec. We have seen something like this already before, so I don't know why we should save this here. Let me get this out. We have Word2Vec like before. Hello world, hello everyone, goodbye world, goodbye everyone. That's an example you also generated by the LLM, and then we get the vector space representation. Like I did before, after we have had the discussion, I reduced it from 100 to 5. Here you see the example is already based on 10, so that we have an easier time here to see the fewer number of values instead of that one. Of course, we could do now the other one as well, like, or another one. I usually don't like this at all, that the variable names have the word themselves, right? But we then get now the vector representation for the other words. So basically we now have the representation for every word, meaning we have a number of words, a number of elements for every such vector, so we end up with a matrix. This can be smaller, this can be larger, right? When we have a large text and we have a high dimension, 100, 300 or whatnot, then we have a relatively large matrix. This is something that we have seen before, plays an important role here as well. So a little bit of a more advanced example. So the libraries are basically the same here. Now PCA plays a role that we have mentioned a few times, dimensionality reduction. You see already probably what the use case is, namely to plot this afterwards. There are examples similar to what we had before. Here is a little bit longer, so there are more animals with their, I would say, most likely word, right? Probably a dolphin swim, but a fish swims in general and dolphin jumps out of the water. You see, this is called sentences, and basically this is what defines the sentence. We could now come up with a lot of fill words, stop words around that, but it wouldn't change it that much. So the application Word2Vec, and now we can visualize the embeddings. But here you see we have 100 dimensions. They for sure cannot be visualized. So we go with here the PCA in order to get from 100 to just 2 components here, and show now the placement here in the 2D space. If we as human beings now can generate proper conclusions, if this from our point of view with our eye makes all that much sense, that's debatable, right? This is pretty close here together, but where is the, I think the cat is down here, right? So, but at least we have the techniques available to show them kind of nicely from 100 to just 2 dimensions. Of course, we lose quite a bit there. So now one of the examples or typical use cases, similar words. So let's find words that are similar to, so let's do with dog, gallops, dolphin, horse, swims, koala. We see these are the words with decreasing likelihood. So distance measure, I don't know, probably I've changed this for a reason. Horse looks better, right? Horse, cat, yeah, that's another animal. Gallops, wonderful. Koala, another animal. Climb, I don't know, things. It's of course pretty small data set as we had before, right? Maybe we even go here with just the 3 of them for each of them in here. Horse, right? And here also for the verb. So for the verb, it works obviously better. Climbs, meows, and gallops. These are other words. So I need to adjust the text. So maybe I do it with a dog after all. Dogs, gallops, dolphin, horse, and so on. So embeddings for the transformer model. So now we are coming to, so step by step to the GPT, so the transformer architecture used by GPT. Again, this will be much more simple. Embeddings are used to represent words in a dense vector space, as we have seen before, as we have had already in the NLP Basics notebook. Beyond keyword embeddings, the transformer introduces additional embeddings to facilitate what characterizes it, namely the self-attention mechanism. The query Q, key K, and value V matrices. So here we get the explanation. So represents the current word for which we want to determine attention scores. It's like asking for this word, how much should I attend to other words in the sequence? So is this more important, less important, right? So this is the question that is answered here. The key represents all the other words in terms of determining their relevance to the current word, the one represented by the query, right? So here, this might be above, I don't know, the dog. Let's stick to the dog. And then we have maybe the words barks, blah, 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 here in the key part. Value contains the information from the input words that we actually want to sum up in the attention mechanism once we have determined how much to attend to each word using our Q and K matrices. So the V vectors are then used to compute the weighted sum. How are these derived now? Based on the embedding. And then we have weights matrices. So embedding is always a starting point here, right? And then we have the weights matrices, and they are learned during training. So in order to get something sensible out of that, what is described here in abstract terms, there must be some training. And like we are used to, weights, objects, tensors in deep neural network. So we have here weights as well. WQ, WK, WV. Simple Python example. We want to embed hello, and the embedding is here hallucinated. It's simply postulated. Embedding hello is 0.1, 0.3, 0.5. Then we have the matrices for Q, K, and V. So we see here this is all reduced to 3 dimensions. WQ, WK, WV. So we have the also hallucinated example matrices. And now the Q, K, V values, these are single values, are calculated, not values, these are triplets here, 3 values, 3 dimensions, what I was saying before, are calculated. So we get 3 arrays, not single values, not floating point numbers, rather arrays that contain each of them 3 floating point numbers. So the query output for hello, the key output for hello, and the V output. So in the simple example, these matrices are the result of multiplying the embedding hello by the respective matrices. In a real transformer model, these matrices obviously would need to be learned, and hello embeddings would need to be derived as we did it before. So the one thing is what we do first, and the other one is what is this pretty expensive task, which costs maybe in the millions, if not hundreds of millions. So transformers and attention, a simplified overview. So we know by now that this is from attention is all you need. That's the core idea, right? Attention at a high level allows the model to focus on different parts of the sequence when producing an output. The intuition is that not all parts of the input sequence are equally relevant for a given input. Attention provides a weighted sum of the input sequence. So if you want to try to find an analogy, what we have done, for example, with our machine learning, but also with ordinarily scarce regression, we could find an analogy here when we, for example, have historical lags price-wise. We recall that I had also opened the trading app with the candles, right? It lags a little bit, right? We would usually assume every candle is relevant, but here with the words it's somehow different. But we could say something like we have a look at the last 15 candles, and the attention mechanism now attaches scores on every candle. What linear regression would do, right? We have what we have seen close to 1, that's the only relevant thing. So attention would be paid only for this one leg to this one leg, and the rest is irrelevant. But of course, then, I don't know if I've shown this when we used I think I didn't do this was part of the exercise, and I didn't implement the ordinarily scarce regression on the log returns. There we would get like for 5, 7, 10, we would get regression parameters that are simply different. So we could, in a simple analogy, interpret this as attention, where we say, well, the lag data, the one lag is much more important than the other one, right? And important here, then I would say, in this simple context, this is what intention is about. And here it's, of course, much more involved than a simple or less regression. And we have here the cat set on the mat, right? The goal is to understand which words are most relevant, and we now need to, whenever I want to click and that, it jumps in there, need to maybe come up with some made-up attention scores here, right? And when we visualize this, that's pretty simple, right? We would say these could be regression parameters, right? Could be. If I leave out what is down here, of course, these are words now, right? But this could also be feature values, right? But there, this is just a visualization saying, well, cat is here, yeah, pretty important, we should pay attention to on mat. So these three together, is what we need to pay attention to. The, and sad, probably not. So the and the here, I would put maybe at 0.5 if I would invent this. Sad at maybe 0.1, but the cat is really at the core, it's about the cat. And on, mat, this is what gives the meaning, right? So on and mat it's not under the mat, right? So cat mat, or the cat destroyed the mat. So here on mat gives us the very meaning. So the attention score calculation, we see here again our elements, the major elements from before. We have started before with the embedding, then we need to compute to train the weights for the QKV values or vectors here rather, right? Then we calculate the attention score and compute the output based on the soft max. Oh, it's nice. I think I haven't read this before. Softmax, a verb form of softmax, right? So pretty straightforward now when we have now, instead of what we have been doing before, a random embedding. Of course, we could use again what we have applied, where to, back, etc. We have the not learned weights, again randomized weights here in the matrix, 2 times 2, and the calculation of QKV as we have seen it before, right? There is the embeddings vector, right? for word vector in embeddings items. So it takes here from the dictionary, iterates over it, and calculates the dot product. Right? Raw attention scores now with the softmax, and then we get here. Of course, this changes. Bunch of random numbers, so this might change all the time. It has obviously fixed a seed here, right? 42, the answer to everything. And we'll repeat this here a couple of times every time we get something else, because it's not trained, it's not learned what we do here. The linear algebra part, of course, is deterministic, but everything here, if you don't fix the seed value, is random. That's the basic structure already, right? To embeddings, we have weights to calculate the QKV values, here our W, etc. pp. Do the computation, a little bit of a soft maxing, right? And then we have our attention scores, right? There is the with the seed should do the calculation. So this is the relevance of each word now in understanding the context of set. Since the numbers are relevant, are random, the relevance here is to be seen with a grain of salt, obviously. Right? So final attention score here, simple calculation. Right? So the complete code now, if you like, is this kind of like now the summary for the basic elements, layers, approaches that are at the core of the GPT model. It doesn't do prediction yet, etc., but this is what is at the core of the engine, which then is able to do all the tricks that we have used already a couple of times. So I promise that we are going to use BERT for a use case as well. So this needs to be installed separately. I don't know if this was via Conda. I think this might have been via Transformers, via pip to install this. The auto tokenizer, and this is what was before the pre-training part. So once we have such a model, we don't need to repeat the exercise all the time to do the same stuff over and over again. So BERT base case, auto tokenizer from pre-trained, right? And here we have the little text that I came up with, again, in between. Python is a first-class citizen in AI world. The AI world is great. So we do the tokenization now. And what we get here is you see the structure is a dictionary with input IDs. And then we have here the token type IDs, all 0 here, and the attention mask, all is 1. So I can now do this also when I'm working, as we did throughout with TensorFlow, apart from the scikit part. So usually it's TensorFlow or PyTorch, here TensorFlow. I can get this in an appropriate format for TensorFlow directly as an output. So we don't need to do any transformation with regard to the format itself. So it is hot in here, this is cold, what a great weather. That's now 3 of these, right? And what I want to visualize or to illustrate here is that this is a situation that is obviously common, that we have different sentences here that we want to have tokenized as before. And speaking of tokenization, right, when we have a very small text, we might have only 10 words, then our tokens might be 0 to 9. Here you see this word has the number 23,334. So the vocabulary of BERT obviously, and makes obvious sense, right, is much larger than when we have a small text. So this is what gives the numbers here for the tokens. Some are lower numbers. I would say these are the more frequent ones. And here now with the 3 different text snippets, we can easily see that the first one seems to be the longest. And here we have zeros. And this is the padding functionality. Let me take this off because these three sentences have different length and it doesn't allow me to do it here, right? Can't convert non-rectangular Python sequence to tensor. Right, down here even more. Unable to create tensor, you should probably activate truncation and or padding with padding true. Truncation true to have batched tensors with same length. So that's something required. Think of it like our supervised learning example, the matrix, the number of features must be the same. Whether we fill it up with something if we have missing values or whatever, but this must be a rectangular matrix. And here with the sentences, it's not possible to do so, and that's exactly why we have this parameter padding true, and it is here filling up now with zeros simply. So 0 as, let's say, a non-token. Right, 101, what is 101? Here, where are the threes of them? It is what, right? So we could now compare, but I'm not going into the vocabulary itself. Also here the attention mask, that's important because it defines to which tokens the algorithms later should pay attention to, and obviously here, since this was just padded, this should be ignored, right? So here everything is relevant, here the final two are not, they are 0, here as well. So this is padding, so filling up, if you like. We can do padding and truncation, which I think here doesn't give us a difference, but yeah, this is what I was looking for. When I do truncation, first padding, then truncation, I set the maximum length to 4. It just goes here with the first 4 that we have. It's not necessarily the first 4, as you can see, right? Here we got the 102, 102, 102 as the final one, right? And a few from in between. So this is what truncation does. At least one thing is clear, it's absolutely clear cut. When I set the maximum length to 4, we just get 4 columns here for the array objects, or here the tensors. Different objects, but in many instances, very similar to the NumPy and the array object.
Wait, you said it's not always the first 4 words? It should always be the first 4 words. It's just that the 101 and 102 signify that it's the start and the end of each sentence.
Yeah, that's the end. Instead of like a dot, might be a question mark or whatever. So I'm not really sure what different rules might apply here in this context, how it does truncation. It's not like simply cutting up, like...
My understanding is that it's the first 2.
It's the what?
So you said 4, but because it needs to know that it's the start and the end, so 101 it's the CLS token in PyTorch or...
yeah, and TensorFlow, yeah.
So it's just beginning of the sentence, which is a random
token.
Indeed. The first 2 actual tokens, so you would have 1327 and 170 for the last one.
Oh yeah, you're correct.
And
you're correct.
It shows that it's the end for each 2.
Yeah, you're correct. These are simply the beginnings and the end here.
Yeah.
I was seeing this, but therefore I was comparing. You're right. These are the placeholder tokens, right? Thank you for pointing this out. So we, in the end, what you are saying, or we are now discussing, means that we are with this 4, we are just ending with 2 of all the 2 instead of 4, right? So it's pretty small in this context, right? So tensors, IDS, yes, and now on a high level, that's just a summary, which I don't want to go through. As a reference, padding and truncation, this is just a little bit more of an input here. Also the BERT model, what we have used here, instead of the toy examples that we had here, we got the proper tokenization for the models. Yeah, maybe I restart the kernel here, and as a very final thing, so that we might be finished a little bit earlier, because Janet was saying that maybe it would be good to show up a bit earlier there. I have just the final notebook, which now requires a paid subscription, and not only a paid subscription, you also need it's yet another account, or like you need to be set up for the API access. As far as I recall, it's a couple of months back with your payment methods, etc. And when we got started and used it heavily for the platform, we ran into limits. We used it for all the videos, for everything. And I was willing to pay, but they didn't allow us. Even, we provided the credit card. Said, no, you reach a limit of 100 US. I said, well, what's 100 US? We need more, right? And then I applied for more. I said, like, 250. I didn't have a clue whatever we would need. And this was also used up quickly. And I said, yeah, I need no, not 500. That's not, currently we cannot provide you that limit. You need to, I don't know what. And in the end, after they charged the credit card for the first time, so they saw obviously that everything works out, then we were able to increase it. So, but on a relatively small level, probably it's pretty easy to set this up. You just need an API token. I also have used for Clarity here that I used a few times yesterday in the beginning. I've also provided a token, but here on Python with the OpenAI package, it's as simple as we have done it before, but now we can write it. Like you have seen the little example that I highlighted on the command line, this little tool. I might try this out. Seems to be pretty straightforward. LLM, and then you put your text, and he was writing, you just need to provide, like with the other API access mechanisms or tools, just your API key. Here we have a selection of different models. It's not GPT-4 or GPT 3.5. There are also a couple of older ones. There is a page on the documentation website of OpenAI which ones are available. I go with the GPT-4. Of course, it's different pricing, right? So the GPT 3.5 Turbo, blah, 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 has something else, 16K as the contact space. That's the cheaper one, the fastest one, or one of the fastest one at least, and still powerful enough. But once you need human-like reasoning, this is what I say, you should use the GPT-4 in this context, right? So I provide the key, and here's just a little helper function where I do some printout. I retrieve text for a prompt. So I said it, so with regard to hallucination, when I started testing this, summarize the life of Dr. Yves Hilpich, only include details that you're sure about. Sometimes when you don't add some qualifier like this, you get amazing and crazy stuff. This is, and here, with regard to my wife, this was also interesting without the qualifier. This was an interesting CV, right? She suddenly also was a Python guru and has studied and a PhD and whatever, right? So, didn't I execute that, or did I miss something? You see, I don't have that much more here in this final Jupyter Notebook. Sometimes the hitting of the API, depending on the traffic, obviously, might take a little bit. I might have gone with the other model, but I want to get the best one for that when it's about the truth or not. So let me see whether it has included any type of hallucinated stuff. You don't figure if here I was born and raised in Germany, that's true. In the meantime, I was born in Bonn or something, so I was never really in Bonn. Undergraduate in mathematics, he's a founder manager. That's true, that's true, that's true. He's also author, that's true, that's true. That's true, frequent speaker, that's true, conducted. I'm surprised so far I couldn't see anything wrong here. Busy schedule, active to the open source community, development summary, fantastic. So, over time in many areas, I see that it has really improved, right? But you see here the qualifier, without it, I don't know what it would have gotten. So maybe I'd try it with my wife. I also obviously know the whole CV, I think so at least, right?
I absolutely love how the AI determines how word things, despite his busy schedule. It just wrote all this stuff about you. It's like, yeah, he seems busy.
Yeah, that's he must be busy, right? doesn't appear to have a widely recognized public figure, so there's no. Here it acknowledges this now, but I told you, I got CVs from my wife that was like really crazy shit, and of course the final 2 questions. What does least squares Monte Carlo do in option price? I mean, these are just like the final things, because I think in the future we will make use of that stuff no matter what we do much more often when we execute code. And they're also now, how shall I call them, embeddings or add-ons or plugins for JupyterLab itself, where you can ask that stuff on the fly when you're coding the Copilot things. This is something that I was trying to, and I must be honest here, so I stopped trying more, wasting more time. I thought that solving tic-tac-toe, who has seen the film War Games from the 80s? I mean, I have seen it as a kid, so I think 1984. And there the machine is playing tic-tac-toe against itself, and in the end realizes, there's no, you cannot win it, and this is translated to the atomic war and the threat and everything. So, but tic-tac-toe, everybody has played it for sure, and I thought this must be a pretty simple example to be solved with Q-learning, reinforcement learning, but I wasn't able to come up with. And there are articles, there's also one guy who said, well, I've spent hundreds of hours, I don't know what the number was, here are my steps, and the final result is not better than some random whatever, right? So, therefore I was asking why it is so hard, and it's saying like, sometimes the small things are just overfitting, and this doesn't really work with these very simple things and sparse rewards, and somehow, that's a little bit of a background story why I'm asking that question, because I have spent quite a couple of hours, and I got some results, and they were better than random play, but not really. I would have thought with a little bit of tweaking that a reinforcement learning agent would learn this thing after a couple of rounds, and they couldn't find. Usually, you then go and say, well, there's somebody who has solved it, but I couldn't even find something. So maybe if you final thing, give it. If you're on your way, if you come along something that might help here with that, I would be happy to just close that chapter for me personally. No sleepless nights these days anymore, but when I was working on it, so in my free time, I don't know, didn't get my head around. In any case, I think we now have covered quite a bunch of things, and still I'm amazed. I get like tears in my eyes when I see ChatGPT creating stuff. This is still for me like magic.
Have you tried using Llama 2 or things like that where you can run them locally instead
Yeah, I
of?
was gonna ask that exact same thing.
No, I haven't, to be honest. So apart from doing all that stuff, I have quite a few other things to do. So my regular stuff and schedule and down-to-earth finance and Python. I would love to, well, currently we have been focusing on other stuff, to be honest. Therefore, I'm, like with the book, I'm not making progress as I'm used to. But we will do for sure quite a few things. But what I can say, and I don't know, I think I haven't shown them, maybe there's one final thing which I'm pretty happy about. Not really proud, just a little bit proud, but actually much more happy about. What we can do with the API-based access and the large language models on our platform, like what I was mentioning, and I showed you the numbers right here for every video. These are like the last 3 sessions that we had. It's the current class. It's called PFF, Python for Finance Key Skills. And whenever a video is uploaded on the platform, there is no code which gets the video transcribed, and then GPT is applied to write summaries, and the whole transcript is stored in a database, and we have this searchable now, right? We have even implemented, and I don't know, I can show you this. So here, this alone, like a summary for the videos, I was also kind of lazy to write more detailed stuff. here it's simply doing it, right? I upload it, nobody has something to do with it, right? Simply shows now the summary and it's all searchable. And when I search, for example, here, is it in there? Yeah, for pandas, let's say, we will get a gazillion hits. This takes now a while because it goes basically through all the different types of contents and the millions. One search about, it's only in personal notes, right? So to every video, everybody can do personal notes. Here, for example, Python for Finance Bootcamp, May 2023, video number 3. And you see here ecosystem, and these days it is, I think, primarily pandas because it's so strong. So it's not only that you see that in this video pandas is mentioned, here 1, 2, 3, plus 33, it's mentioned 36 times, 2.5 hours long here, and you can jump simply, could provide the URL, and pandas was retrieving the data from the remote source, right? So here I can here click on the link with a timestamp, and it opens the video exactly at the timestamp where the word was mentioned, right?
The issue now is that you're passing all this through ChatGPT, right? So that
Yeah.
now
Through GPT-4. Sorry?
ChatGPT can be trained on this.
Could be, yeah.
So then they can provide that information.
Python was retrieving
out for
data
free
from the
to
remote
you.
source.
So is that a,
So I'm now going to
is
use,
that a concern or? Because this is private information, right? You don't want this to be given out.
Yeah, it's basically, it's not private in that sense, right? It's in a semi-private domain. Right? Yeah.
I mean, if you uploaded it to YouTube, even on a private thing, it's still gonna likely get turned into, like, the transcript is still likely to get generated somehow on the dataset anyway.
Yeah, so the only option would be like what we were saying, we run it maybe not locally, but on a server, Llama on our server, do this all on our own, but it's like with the books, right? The books are out there as well. It's trained on the books. It's trained on my GitHub repo with regard to the code. I see many, many more benefits here as compared to any other concerns. But of course, in the beginning, I discussed it with, in particular, one very good friend of mine. I don't know what the future will be in this regard. There are a couple of lawsuits going on, and maybe currently the lawyers are using ChatGPT to prepare their cases, right, on the one side and on the other side. I don't know. Overall, for me, there are a couple of concerns, AI risk and privacy and copyright. But for me, the excitement and the opportunities are like here, and like the rest is down here. So therefore, I see issues. And basically, when I got started yesterday, this was one of the first things that I mentioned, right? That it's trained on my stuff, but it doesn't provide any reference in this context. So how is this to be handled? How, right? I ask it about something that maybe a context, specifically the one package that I mentioned, and I get back now something, who is attributing what to whom and how, and you know, is this like this endless mirroring when you share your screen or what, the camera? I don't know. Again, for me, absolutely exciting what we have here available, what we can do these days. It's fantastic. I hope they make it even better with everything that they have added also now with the visuals that you can generate within ChatGPT. And you see at which fast pace this is getting better and better and more comprehensive and with more capabilities and skills. So I'm looking forward into a bright future, having not really, maybe I'm old enough to not be too afraid of like being replaced immediately, right? So there are other people, and when you think back, there was always the big fear that blue-collar workers would be replaced by robots. No. It's the white-collar workers here, the thinkers in the end that are getting replaced by these models. But again, I think it's more of a positive outlook for me in any case, and I'm still. You might have noticed I'm pretty excited about all that stuff. So hope to see you sometime soon, maybe back here, or maybe online or wherever. Or now at the barbecue.
Yeah. You